Covalent bonds. So Gilbert Lewis also suggested that molecules could share electrons. So we can take two hydrogen atoms and they could share their valence electrons to form their complete noble gas stability. Covalent bond then is a bond which two electrons are shared by two atoms. A covalent molecule is a compound which only contains covalent bonds. A shared pair of electrons is usually shown as a single line. So instead of drawing dots, we would just draw a line to show that those are being shared between the two hydrogen atoms. In fact, it's better to use lines than dots when drawing Lewis structures, so it's easier to identify the electron pairs. We're only concerned with the valence electrons because the core electrons are held too tightly to the nucleus to be shared. A lone pair is a pair of valence electrons that are not involved in the covalent bond formation. So a Lewis structure is a representation of a covalent bond in which shared electron pairs are shown as lines and between two atoms, and a lone pair of electrons is shown as a line on an individual atom. Now we draw these lines to represent the octet rule. An atom, besides hydrogen, tends to form bonds until it's surrounded by 8 valence electrons. Hydrogen just needs 2 valence electrons to be like its closest noble gas, helium. There are some exceptions to the octet rule, but we'll talk about those later. So a single bond is when there's 2 atoms sharing 2 electrons. You can have multiple bonds, double or triple, where you'd share more than just 2. The bond length is the distance between the 2 atoms of the covalently bonded molecule. So the more bonds that you have between 2 atoms, the shorter the distance becomes. There's more overlap in their orbitals, so they become closer together. So if we were to look at these 4 examples, CO2, we would have carbon in the middle, double bonded to our oxygen, and then our oxygen would have lone pairs. Nitrogen, the diatomic, is a triple bond. C2H4, we would have carbon with 4 hydrogens evenly distributed, which means our carbon has a double bond. C2H2, we would have our carbons and 2 hydrogens evenly distributed, so our carbons are triple bonded. So if we think about the bond length, nitrogen and our carbon triple bond would be equal to each other. They would be shorter than our carbon double bonded and our oxygen double bonded to carbon. And those would be shorter than our carbon hydrogen bonds. So the more bonds you have, the shorter the bond length. If we were to compare covalent molecules to ionic compounds, the difference in the properties is the difference between what's holding the molecules together. So ionic compounds are held together by electrostatic forces, which are stronger than the forces holding a covalent molecule. Now, covalent molecules are actually held together by 2 different types of forces. You have the bond enthalpy, which is the 2 atoms bonded together's force of attraction. And then you have intermolecular forces, which are the forces between different molecules. So ionic compounds tend to be solids, where covalent tends to be liquid or gas. The melting point of ionics are high, where covalent is low. Boiling point of ionic is high, where covalent is low. Solubility in water is good for ionic compounds, but it tends to be low for covalent. In fact, if they do dissolve in water, they are non-electrolytes because they don't separate into ions. Conductivity for ionic compounds is when it's melted or dissolved, but not when it's a solid, and that's because we have to have the free moving electrons in order for it to conduct. Covalent molecules don't conduct because they don't have those charges. They're sharing electrons, not transferring them. So they're actually called insulators. Now, electronegativity we can use to also explain some of the unique properties of covalent molecules. Molecules which are sharing electrons between identical atoms should share them equally, or be nonpolar. But a polar covalent bond, the electrons spend more time in the vicinity of one atom than the other. So we can think of this as a partial electron transfer or a shift in electron density. So down here we have HF. Fluorine is more electronegative than hydrogen. So this red area is telling me that I have more electrons hanging out on this atom than this atom. So my electrons are shifting towards my hydrogen, towards my fluorine, leaving hydrogen with a partially positive charge and my fluorine with a partial negative. So we can show partial charges by using a lowercase delta, or we could draw this arrow, or we could look at an electron density. Electronegativity is the ability of the atom to attract towards itself the electrons in a chemical bond. It's related to electron affinity and ionization trends, so the values have no units because it's relative. It's not measurable. The trend for electronegativity is an increase up and to the right. So fluorine is the most electronegative, where francium is the least. Notice that on the chart we also have krypton and xenon included, and that's because even though they're noble gases, they can form bonds, and we'll talk about that when we talk about the exceptions to the octet rule. Now, ionic compounds, their values would differ widely. Polar covalent, their values would be more comparable, but there would be a shift in electron density. Not completely, but a small shift, like in our FH. Nonpolar covalent or pure covalent bonds, they really don't have any difference between them. Now in Chem 1 we actually subtract values, but in AP you should be able to use the periodic table to figure out what it would be. So ionic compounds widely differ, so they tend to have a value of 2.0 or higher. Polar covalent would be a difference between 2 and 0.3, they're a little closer together. And nonpolar would be 0.3 or below, so it's really just when it's the same atom. So if we look at these examples, which one is covalent, polar covalent, and ionic? CSCl would be our ionic compound because the electronegativity values would differ widely. So for cesium, if we look back, cesium has a value of 0.7 and chlorine has a value of 3.0. So they differ widely. In fact, if we calculate it, it would come up to be 2.3. H2S. Now we're just talking about the bond, so the fact that there's two hydrogens don't matter. We're just looking from hydrogen to sulfur, what would happen. Well, those values are a little bit closer together. They're both nonmetals, so it would be polar covalent. In fact, the actual values are 2.1 compared to 2.5. So that would give us a difference of 0.4. Now, again, we're just looking at the bond, so it's specifying for us to look at the bond between the two nitrogen atoms, so we can ignore the hydrogens here. Now, that's the same element. So this would be a pure covalent or nonpolar covalent because both of them would have a value of 3.0, so the difference would be 0. Electronegativity is different from electron affinity. Even though they're related, since they're talking about the tendency of an atom to attract electrons, electron affinity refers to an isolated atom's attraction for that extra electron, whereas electronegativity is the attraction for the electron within a bond. So electron affinity values are experimentally measured, but electronegativity values is an estimated. So electron affinity has units, but electronegativity does not. Electronegativity also helps us understand oxidation numbers. Now we talked about oxidation numbers back in Unit 4. So if we think about NH3, we said hydrogen next to a nonmetal has an oxidation number of +1. That would give us a total of +3, so that means our nitrogen would have a -3. Well, if we look at the structure of NH3, nitrogen, being more electronegative, is going to attract the electron from hydrogen more often. So that means my nitrogen would have a partial negative coming from each of the bond. So that's partial 3 negative, so that's why it's a -3 oxidation number. Each of my hydrogens then would have a partial positive value. So that's why each of my hydrogens is a +1. So here, looking at our electron densities, which would represent these 4 compounds. Well, NH3, we said that nitrogen would carry the negative, which is shown by the red value, so this is partial negative, and then my partial positive is hanging down here with my 3 hydrogens, so this would be NH3. Now CH4, carbon is more electronegative, so in this picture we have our red hanging out in the middle, so this would be our delta negative, and then on each of our 4 corners, and that corner is in the back there, would be our partial positive. So this would be CH4. HF, we already said F would be my delta negative, and delta H would be, or delta positive would be my hydrogen. So this would be HF or FH, leaving water to be this one. So we have our delta positives for our hydrogen and our delta negative for our oxygen.